Good morning. Thank you all for joining us for this fourth webinar that ACT-IAC has organized highlighting the President's Management Agenda. Today's webinar will feature a discussion encompassing both data and modernization. For those of you who have joined us in the past, thank you for your attendance again, and for those of you who are new, welcome. The Institute for Innovation within ACT-IAC works to highlight exciting over-the-horizon innovations within the private sector and in government. And as part of this mission, the Institute sponsors an award program called Igniting Innovation, which happened this last May. Today's presenters from Precise were one of our Innovation in Healthcare Award winners from the event for their innovation called PillSafe, and we're delighted to have them today. This was a new category that the Institute for Innovation recognized at Igniting Innovation, one that is both timely and relevant within the United States today. The Institute is proud to present this webinar, and we look forward to highlighting some more Igniting Innovation winners in the upcoming series of webinars. So please stay tuned for more information on that front. And a special thanks to ICF and to my colleague here, Razik, for helping me organize this today. And before we begin, I'd like to ask you all to feel free to submit your questions using the Q&A box on your screen. We will make time at the end to address as many questions as we have time for us. With all that said, I'd like to turn the discussion over to the PillSafe team and to Ben for their presentation. Thank you all.
Oh, thank you, Mark. So let me flip to the next page. You all can see the change, right? Slide change, right? Mark.
Sorry.
Can you see the slide change? I just flip to the next slide.
I'm not seeing the slides.
Okay.
Yeah. Okay.
Just want to make sure that all the logistics is set up. So for the folks on the call, can you guys see? I've tried to flip to the second slide. Can you guys see it? Yes. Okay, great. All right, good afternoon. This is Ben Duan. I'm the Chief Technology Officer of Precise Software Solutions. We're so honored to be here and to present to you some of our innovation product ideas to addressing the health and food safety concerns. And thank you so much, ACT-IAC, and the special Mark to invite us to be here. So just a little bit of introduction about who we are. Precise, we're an ACT-IAC certified consulting firm, primarily focusing on providing consulting service to federal, state, local governments. If you look at the left diagram, that actually showed our main capabilities and the service area. So if you look at the top, it's system modernization and integration. It's by far our largest sector or pillar. We help our customers to upgrade legacy systems and integrate enterprise systems together to streamline, automate the business processes and reduce costs. You please go over the clockwise. The next one is the digital transformation experience. So we deliver the SaaS services, including ServiceNow, APM, Office 365, and also we design, develop, and operate the mobile applications, as well as the portal content management system. And the bottom is our cloud and infrastructure business. We have enjoyed very fast growth in this area, in which we provide end-to-end data center modernization and cloud services, including strategy, roadmap, architecture, engineering, cloud migration, infrastructure code, and establishment of cloud center of excellence. So we provide services in multi-clouds, including AWS, Azure, Google, and Oracle. We're AWS certified public standard consulting partners and Oracle Go partners. In the data management and analysis business, which is on the left, we provide on-prem cloud transactional database design and data warehouse design. In addition, we deliver data analytics services, including AI, machine learning, and lately the blockchain. We have enjoyed some very exciting innovation in this area, and some of those will be presenting to you in this webinar. We also provide strategy consulting services wrapped around our core technical capabilities to provide agency senior leadership of IT strategy, just-in-time, just-enough enterprise architecture, new technology adoption strategies to drive agencies' mission and achieve business objectives. We have very strong relationship with some of the world leading innovation product companies like AWS, Microsoft, Google, Oracle, VMware, etc. So in the last few years, we have enjoyed double-digit year-over-year growth and have enjoyed quite a bit of industry and government recognition. Most recently, our firm was recognized by U.S. Senate Small Business Committee as U.S. Senate Small Business of the Week. Senator Ben Cardin recorded a video to recognize us. Our founder and CEO, Dr. Zhenzhen Huang, was also recognized as the Small Business Person of the Year in Maryland in 2019. And one of our innovations, the PillSafe, was selected among the top 8 innovations among the 200 plus applications in this year's ACT-IAC Innovation Award. We did not get to the top, but we're very close. So let's get to the meat now. In this presentation, I'd like to introduce you how we use the latest machine learning technologies to help solve some of the health and food safety concerns. So my colleagues, Dr. Xin Liu, our technical director, Ms. Alan Creighton, our executive enterprise architect, and Ms. Romain Boss, our data scientist, will present you the 3 innovation proof of concepts. We're pretty excited about the ideas and solutions we developed and have filed 2 patent applications. Without further ado, let me give you Dr. Xin Liu.
Thanks, Frank. This is Xin. I'm the technical director from Precise Software Solutions. So today we're very excited to present a couple of solutions. So the first one is the PillSafe. As you mentioned, PillSafe has been awarded, the top 8 for ACT-IAC Igniting Innovation event. So just to let you know, this is our product produced last year. And my colleagues will present a much more exciting product later on. So let me go through this one. So the PillSafe is, in terms of the PillSafe, we try to resolve the post-marketing medication. So as you know, U.S. and the world spend a lot of money on drug safety side. So most of the money is spent on the pre-market, all the clinical trials, to make sure the drug is safe, is effective. But for the post-market, there are very less efforts, I would say, until today, put into how to monitor those drugs and how to make sure the patients got enough information around those drugs and get more information to help them to make a decision and to improve their health conditions. So with that, we came up with the idea of the PillSafe. You can see here there are a lot of numbers here. So by statistics, this is a number from 2016. So there are 187 million Americans use prescription drugs every day. And it's pretty much equal to 58% of the population. And out of those people, 110 million people a prescription drug that has never been picked up, right? So it doesn't matter how much effort we put into the pre-market, but we still have 110 million prescribed drugs that has never been picked up. That means the patient didn't get the treatment, and 50% of the patients they didn't take the drug on time as prescribed, and as a result, there are 125,000 people died because of that. So you can see there's a huge risk on the money and also on the life. So folks, we just learned that you can't hear us very clear. Just want to make sure. Is that getting better right now?
Yes, it's better. Thank you.
Okay, sorry for that. Thank you. Okay, so in order to target those issues, we came up with this idea called PillSafe. PillSafe is a mobile application, but at the back end, we run a lot of cutting-edge technology. For example, the whole infrastructure is running in the cloud. And also, we use a lot of machine learning, artificial intelligence running at the back end. For example, I'm going to demonstrate one of the capabilities to use machine learning to do the pill image recognition. And also we run the background algorithm to detect the adverse event, try to extract the real signal from the patient reported event. So for PillSafe, we provided multiple features over here. You can see the first one, the most important thing is the medication management. So we give the opportunity to the patients to use this application to manage their daily medication schedule. So they can register their pills and schedule what time they need to take those kind of pills. And when the time is coming, the patient will get either in-app notification or text messages to tell them to take the medication. And also, we provide much more information around the drug they're taking. For example, we provide the drug recall information. We provide the black box warning information if there's any. And the most important thing is we give the information to the patient regarding the drug interactions if the patient takes more than one drug at the same time. So you can see, actually, we were surprised at how many interactions were there, tied to multiple drugs. And also, one of the intentions is to align with FDA's approach regarding the post-market, right? So right now, the most hot topic in FDA is talking about the patient-reported outcomes. So traditionally, all those adverse events or side effects is reported by the medical facility. But using this app, we give the patient opportunity to report by themselves. So the patient, they can use a simple form to report their daily effects when they're taking medication. For example, if they have a headache, dizziness, and so on. So we take all those information tied to the patient's records. And also we're trying to running the machine learning algorithm at the back end to extract the real signal to detect if it's a real adverse event. And of course, we're considering the patient's privacy at this moment, right? So those data we only collect those data based on the patient's approval. So the patient has the opportunity to choose if they want to share the data or not. And also we provide additional information like clinical trial based on the patient's condition or the drug they're using. And also we provide generic drug options to the patient if they have some financial considerations over there. And the last but not the least, we provide a social media connection to the patient. So based on their medication list, we do algorithm at the back end. We figure out what kind of disease that they belong to and what kind of social group they should join and get more information regarding their medications, right? So we connect this app to the social media such as Twitter, Facebook, Yelp, and to give much more information, not exactly the professional medications suggestion, but get the information from the regular users. So one of the features we provided through this app is called pill recognition. So we were thinking, for the outer groups, right, the patients, so they find a pill and they don't know what it is. And what if they want to know the suggested dosage or suggested frequencies of taking those pills? It's hard to find this information. So we leverage the machine learning method to allow the patient to take a picture of the pill, and so we use our trained customer modules and figure out what kind of pill it is, and present all the information around this pill to the patients. So we can identify the drug's name, and we can identify, if this drug, after taking the picture, we can identify if this drug is already added to the patient's list, and we provide drug information such as, suggested dosage and if there's any drug interactions. And also, we are taking images from NIH image library, and we were thinking, since we're taking from the government, we should have the obligation to contribute to the government's library. So we have the idea of collecting all those images and send it back to the NIH to replenish their existing library. So this is a high-level machine learning vision process for model training. So we are using Google the latest platform is called the Google AutoML Vision platform. So this is a very high level how we train the model, how we use it. The first step is to do the data collection. Then we do the data labeling to make sure the image tied to each individual ARC-CUI ID to that drug. And then we do data augmentation to rotate the image, to zoom in, zoom out to make sure the model is fully trained. And then we do the model training in the cloud on the Google AutoML Vision platform. The last step is to use the mobile application to connect to the AutoML and to do the prediction. So this is represent the process we're doing the image augmentation. You can see there are 3 steps. First of all, we took the image from NHP library, and the first step is to crop the image to make sure we are getting the exact image and to make sure it is on the correct size and correct face. And the next step is to rotate the image because if you're considering the pill, the imprint on the pill, we need to rotate it to capture all the angles. When the patient is taking the picture, the angle should be covered. And the last step is to zoom in, zoom out to get the image and to make sure, to replicate in the real time when the patient takes the images. So as a result, after image augmentation, we converted the one image into about somewhere around 200 images for model training. So this one is very high-level pictures about how do we use a Google AutoML platform, right? So the first one, step one, is to prepare the image. So after we do the image augmentation, we converted one image into 200 images. Then we upload it to the Google platform. The second step is very simple. It's just a matter of to click a button to train your model. After you train your model, you can use a cloud platform to do the prediction test, or you can use the mobile application to connect to this Google platform through the regular REST services call. So here's a very short demo we want to show you. It's about our application to show you the process of doing the image recognition using the mobile application. Give us a second. So they started, for the patient, they can, when they try to add the drugs to the list, they can do the regular search by typing the... Hold on one sec. So I guess looks like you guys won't be able to see it. Can you guys see where kind of play? It's coming. It's coming, right? So okay, correct. So let's rewind. Rewind and go back again. So when the patient try to add the drug to the list, they have the options to search by the drug name. You can simply type in the drug name, and we give you options to do the selection over there. And the other option is to take a picture of the drug. So you can see there is a camera icon on the top right corner. You click it. You open up the mobile phone camera. Okay. Sorry, folks on the phone. It seems like we have some delay on the video. Let me rewind it a little bit here. Okay. All right. So you guys can see we are taking the image of the pill right now, and you can. Yeah, it's not. We can share this video after this meeting if you guys are interested. I'm sorry, this network connection is not good enough. I think, yeah. Yeah, I'll just go through. Yeah. Okay, so you take an image. If you cannot see the full video, as I said, we're going to share this demo after this meeting. So you can take image of the drug, and then you can, we will find what kind of drug it is. and then give you information about this pill. For example, we have the descriptions and we have the black box or recall information if there's any. So you can see here we're capturing the drug information, and we have the description about that. There's a delay. And after you confirm this drug you're taking, you can add this drug to your schedule. So you can schedule what time you want to take this drug. And when the time is coming, you'll get in-app warning or you'll get a text message. All right. So that's pretty much confirmed. Okay, so that concludes the demo for PillSafe. Now I'm going to hand over to my colleague Alan, and she's going to talk about our newly developed outbreak detection.
Good afternoon, everyone. Can you hear me?
Okay.
Good afternoon, everyone. Can you hear me? My name is Ellen Creighton, and I'm going to present to you AI ML use case using Twitter, food outbreak signal detection. Food safety is all of our concern. It's the concern of government, public health, communities, and of course businesses. As you can see from here, the potential risk and outbreak of the food safety and food poisoning problem is a serious national crisis that affects public health as well as social and economic welfare. Now, with this application, we have actually put forward an application that is well defined to address this problem, at least to help the public. The application was designed using Google's latest natural language model called BERT. BERT, of course, as you can see, is bidirectional encoder representations from transformer. Very long name, but we'll give you an idea of how it works through a workflow, and at the end we'll give you a small demo. I will now move to the next page. So let me show you how this works. The individual, as you can see in the picture,
there's some delay over here, yeah.
Oh, sorry, there's a slight delay, so I'm going to wait until the picture comes up. Good. Thank you. Sorry about that. This is how it basically works from a simplistic point of view. The person eats poisonous food in a restaurant or any location for that matter. The person tweets, "I ate beef at a Chinese restaurant in Rockville and got sick." If you look at the bottom, you will see the address. Now, if your location is enabled, the address will be, will actually show. In some cases, there are no locations, and that information is not shown there. However, the next stage is that information is reported into a statistical food poisoning which collects it in all of the United States. Now, this application can be applied to anywhere in the world. However, our focus for this demonstration is the United States, as you can see. And we will demonstrate to you how this map works. Now, you see three colors there. You see blue, and you see gold or yellow, if you want to call it that, and red. The blue means that there are up to 10 incidences in the area of food poisoning. The yellow means that it's from 10 to like 99, and of course the red is up 100 and more. And then that information is captured, and if you can look on the left side of the Google map there, it actually points the location of that capture. The good news is, and I'll tell you a story. In 1996, on October 7th, there was this big thing on TV, and the Wall Street took it up. The drink, Odwalla, Odwalla, actually had E. coli, and there was a huge crisis in Colorado, and not only Colorado, but all over the United States. This company was well known for producing juice, unpasteurized juice, and they pride themselves on it because at the time everyone was concerned about health food. So we wanted unpasteurized milk, unpasteurized juice, and so this particular juice was contaminated with E. coli bacterium. But guess what happened in the case? There was an outbreak. A 16-month-old baby called Anna in Colorado died from kidney disease as a result of drinking this juice. But then 60 persons became sick. And then another 14 children were hospitalized with listeria. Until this day, they're suffering from severe kidney disease and blood disorder. And there is no way of telling if this is going to last them for a lifetime. So I'm telling this story to emphasize that food outbreak can impact individuals, it can impact families in very negative way, as well as community, and most importantly, bottom line, because the company was charged over $1.5 million, which I thought was a small amount for such a devastating situation that could have been avoided. So that's the Odwalla case, and you can find that, you can read the whole story yourself. I want you to move to the next slide, and I will sort of take that slowly so the slide can come up before I go through the flow of that slide. Is it?
I think we can go, yeah.
You got it. Okay, this is really a simplified view, what we call the flow chart or system flow of how the system works. The most important thing is how we gather the training set. The first step is to collect and label 80, in our case, for this particular demo, we have 8,500 tweets from trending data, specifically targeting food poisoning. And we use that data as a model in our BERT system, the BERT system that I just mentioned to you. Once the model is trained, the model then is dispatched into the cloud where we have a TensorFlow server. Now, in real time, our system filters the tweets regarding poisonous food, the feed and the tweet into and feeds the tweet into the BERT model for classification. Now, if the tweet is recognized as food poisoning related, that information will be inserted into the tweet and hence into a geolocation, timestamp, and other information, and it moves into what we call the BigQuery, as you can see there. BigQuery then ensures that information is displayed on the front end visualization. So on the front end, reads that BigQuery in real time displays geolocation information and a tweet with respect to food poisoning onto the Google map, and you can easily have access to that. Now, my colleague, Shin, will sort of give you a demonstration of the Google map to show you how it works. And you will see the three coloration that I told you about, the legends, and he will explain how that works in real time. Thank you. We're prepping the map. Share my screen.
So we're still waiting for the map popping up. Just as Anna mentioned, our intention for now is to monitoring the food outbreak in U.S. only, based on the data we're getting from Twitter. And we do have a plan to incorporate more data source in the future. Actually, we're working on it right now, so we're going to take the feed from Facebook, Yelp, and all those possible data sources. But for this case, we'll only take the data from Twitter. So you can see here, Anna just mentioned we have different colors of the circle over here. Different color means this, density of the tweets, right, related to the food outbreak information. You can see on the Oregon side, we have 11 tweets related to food outbreak at this moment. And you can see there's a red circle, 366 tweets. It's in the ocean. By the way, it's not in Bermuda. It's not on the cruise ship. It is because when people tweet, right, so not everyone turn on their geolocation.
Right.
So that's the tweet. We cannot identify the location. We group them together and put them over here. But still, we can find a lot of useful information from here. And for this map, you can zoom in, and you can see from here we have different tweets around the Kansas City here. We have 9 tweets here. Let's see what they're talking about. And you can see after click this button, we can see there. Okay, we're still waiting for the.
I'm waiting for the.
Okay. So when we click this blue bubble here, you can see it will pop up all those detailed tweets information and with the timestamp. So we are showing the data only for the last 7 days because we were thinking it's more relevant to the full outbreak. So we keep 7 days data from tweets. Of course, we keep historical data and we can do the trend analysis as well. But for this monitoring, we only keep 7 days data. And you can see all those tweets. You can see what they're tweet about and what kind of issues they have, and where even the restaurants they have issues with. So we can show on this map. If you zoom out, and there's a little bit delay over there. Yeah. So on this map, you can zoom in to or zoom out, and you can find the different information for these different geolocations. And also, we provide this filter functionality. So you can see here, let's wait for the video. So if you click the filter keywords here, we can filter all the tweets based on the nature of their tweets. So you can see, for example, you want to see who is tweeting about avocado at this moment, and of course they have issues with avocado. You can see only 3 tweets out here, and if you click California, let's see what happened there. So somebody complains they ate sushi, and they're going to throw up for the taste. And also you can see there is a keyword talking about avocado, and so we're capturing that one. And also you can filter by your medical conditions. So if people have a problem with, let's see, kind of medical problem they have over here. I'm not sure if you can pull up the data. Apparently, there's no data about this condition. But if you go to comments, let's see how many people throw up. You can see, there are a handful of people that throw up with this condition. So, in short, we provide this very simple map user interface for people who is interested. And, of course, we can find the outbreak information from this map. If there's an outbreak happening in a certain area, you can see the bubble is red and a lot of related tweet about that. So we can get the much more relative and quick information from the population. All right, so with that, I'm going to switch over to my colleague, and my colleague is going to talk about our latest and the best product. It's called image recognition, and I'm sorry, the counterfeit drug detection.
I just want to add, so you can see how many instances of the outbreak detection, food detection applications can save lives, save public official time and money, and discovering the source of the outbreak. So that's, I just want to add to that. And as we move to our next presenter.
Okay. Hello, everyone. My name is Romy, and I will present patent pending counterfeit drug detection project. Counterfeit drug problem arose widespread concern in society in recent years. And the counterfeit drug medicine is a medicine containing wrong active ingredients, incorrect dosage of active ingredients, or harmful ingredients. And counterfeit drugs could cause a lot of problems in our society. First of all, it is harmful to human risk. Human health. You know that counterfeit drugs cause health incidents frequently in our society. In 2009, anti-diabetic medicine contains 6 times the normal dose of glyphosate, and this accident caused 2 people died and 9 people hospitalized. And the second negative impact is that counterfeit drugs contains a huge market share. 10% of medicines in the United States are counterfeit drugs, and 25% of medicines in developing countries are counterfeit drugs. This includes substandard medications. The third harmful impact is that it causes legitimate company losses. Civil lawyers is 8.3 million doses of counterfeit drugs in 2010, and we all know that nearly all large medicine companies have a large lawyer team to fight with counterfeit drugs. At the same time, it has a very huge worldwide influence. Let's take a look at this picture. As the Asian area is the most serious, faces the most serious problem. 42% of the medicines in supply chain are counterfeit drugs. Also, the problem is not improve too much in North America, because that nearly 25% of the drugs in supply chain are counterfeit drugs. So our project aims to help customers, pharmacists, and regulatory agencies to detect counterfeit drugs in the market to ensure public health. First of all, we do a market survey about the on-the-shelf counterfeit detection solutions. They could be roughly classified as 2 kinds of solutions. The first solution is chemical component analysis. It's accurate, but it's slow, destructive, and expensive. So it's not suitable for large volume detection process. It takes too long, and also it costs too much money. The second kind of solution is package scanning. It's very low cost, non-destructive, and it's very fast. So that's the reason why we adopt this technical direction. The theory foundation of package scanning is different chemical components have different refraction rate under certain wavelength light. We take pictures of the pill under multiple wavelength light. Counterfeit drugs will show different brightness compared with authentic drugs. Up to now, the on-the-shelf package scanning products, they do compare this kind of images manually. It's very slow and labor-consuming. Sometimes it makes a lot of mistakes. Also, training is required to do this job. So our mission is try to optimize the counterfeit drug detection process. So let me first introduce the hardware architecture of our solution. Our hardware architecture actually contains 3 parts. The first of all is a box. The second one is the cloud, and the third one is the mobile. Our box actually is the core of our solution, and the TPU module is something like a brain. It's the core module in the whole system. TPU is an abbreviation of tensor processing unit. It is a very new kind of processor which is specialized to process tensor data. It could be applied in machine learning algorithms to much shorten the calculation time. We use this to realize real-time reaction. TPU controls a full spectrum camera and multiple wavelength LEDs. Basically, it could control the camera take pictures under different wavelengths, then do detection process. Our cloud actually is used to design the module and train the module. Box will upload a training data set to the cloud and save in the database, and Google AutoML will be used to train the module. After the module is trained, we will deploy back to the TPU to do the detection. The mobile is used for user interface. User could use your smartphone to control the box to do detection. Also, the results will be traced back to the mobile phone to show to the user. That's our hardware architecture. And then I will talk about our solution detail. This is a proof of concept system, and on the left side, this is a picture of our box. It contains TPU, power supply module, and camera and LED. Basically, when in the detection process, it will take pictures and do module calculation to give out the prediction result, and we use Bluetooth to transmit the data, the images to the smartphone, and it will use smartphone to show the customer. The reason we use Bluetooth is that it could be used under no internet environment. No Wi-Fi or mobile data is required to use our system. So we could deploy our system to rural area, developing country, everywhere in the world. And that is where counterfeit drugs will show up very frequently. Then I will talk about the software workflow. Our software workflow contains 5 steps. The first step is we need to obtain a training data set. Basically means we need to take pictures of the authentic drug and do some image processing like cropping or edge detection to prepare a training data set. Second thing we need to do is to build up a model, a machine learning model, something like a convolution network or SVM or something like this. Then we use the training data to do the training to tune our parameters to be the best performance. Then we deploy our system module to the TPU edge. Finally, we could do detection. That is our workflow. This is how our hardware is looking like. On the left side is a picture of our motherboard. We could see on the right bottom is the TPU board, which is this green board. This is the brain of the whole system, and it to control all hardware and do prediction. On the top left is the power supply module. It basically supplies power to all components in the box. In the middle, this is relay module. This is used to control different lights. On the right side is how it really works. It's under UV light. You could see the LED. It's under UV light. The light will be project on the pill, and the pill will do reflection, and camera take a picture. That's how it really looks like. And this is our data. This is our data we have captured under 3 different lights, under UV, visible, and IR. We could see the first left is under UV light. Actually, the counterfeit drug is glowing. It's much brighter than authentic drug. And this represents that brightness difference of counterfeit drugs and a certain wavelength. Also, on the right top is under visible light. It's color difference. That always happens because counterfeit drugs usually have color difference compared with authentic drugs. And in the bottom is IR light, and it's darker. So these three kind of examples is very classical counterfeit drug behavior and the different wavelengths. Also, this is the feature we want to extract to our training model to do auto counterfeit drug detection. And I will talk about the training process. We use Google AutoML to design our model and do the training. The first step is to build up a training data set. You need to upload your data, label them. We could see in our data set, there are 5,000 authentic drugs and 2,000 counterfeit drugs. After you prepared your data, you need to click train. Its model will be auto-designed, and it's based on convolutional network, and it will give you a well-trained model. Finally, you could deploy your model onto your TPU hardware and do prediction. In our prediction process, this is offline, and we self-design a Python package which is called CFDD, which is the abbreviation of counterfeit drug detection. It has two commands. The first is capture. Basically, that means take 3 pictures under different wavelengths, then finish its job. The second command is called detect tons. Tons is the name of pills. You have to have a name for different pills because different pills have its specific model. You need to clarify its name. Then, after you input this command to the TPU, it will automatically do all the things. It will first capture image, which will take a look at the right side. It's the output of our command. It will take pictures and save that to the folder. We have 4 modules: UV, IR, visible, and imprint. Imprint model basically process the pictures to each detection and try to compare if the images we capture have a same imprint and texture with the authentic drugs. So these 4 modules basically do jobs separately. They will give the result if that is counterfeit or authentic. If one of them is counterfeit, we will give a final detection result as counterfeit. If all of them is authentic, it will be a clear path. We will say that is authentic. That's the logic of our detection process. Finally, let's take a quick look at our interface. It's very user-friendly. You could just input name, and it will give you out the result. And it will also give you out images we have taken. So it's very easy use, quick reaction, and no training is needed. So finally, we will talk about the value of our system. It's very fast, easy use, accurate, and at the same time, it's very low cost. So that's our system of counterfeit drug detection. And it's very interesting, and it helps us to fight with counterfeit drugs. Okay, that's all. Thank you.
Thank you.
Excellent. Thank you, Ruben. So this is the slide to summarize the 3 innovation proof concepts we developed. I hope you all enjoyed seeing the demos, seeing what we come up with. With that, I think we're just this is our contact information. If you kind of interested in learning more, this is the contact information you can find, and do reach out to us. With that, I think we open for Q&A.
Thank you all very much for the presentation, and just a friendly reminder to the audience that this webinar will be made available later on the ACT-IAC website and on the ACT-IAC YouTube channel. And a question from the audience, and I think that this is a very good one. What is the accuracy rate of the PillSafe pill identification application?
Oh, I can speak for that. So actually, we do have two models. One is called using the AutoML. You have seen Robin has presented. And the other one is called one-class classification. So different model has different results. I mean, for AutoML, we are expecting more than 90%. PillSafe pill identification. I'm sorry. I'm talking about the, because I'm excited with counterfeit drug. So for counterfeit drug, we have more than 90% of the accuracy. For PillSafe, actually, it's pretty accurate, and we're satisfied with all those information. But one thing we can say is, we don't provide the unsure information to the patient unless we know exactly what it is, right? So we have very high requirements for the accuracies because it's related to the patient's health. So we don't have exact rate. I would say we have same thing like counterfeit drug is about above 90% of accuracy. And right now we're moving on to the next stage. What you can see here is only recognize one pill each time. Now we developed a module, we can identify multiple pills in one shot and give the name for each pill. So we're finalize that design and try to deploy it.
Mm-hmm. So I want to add to that. Right now we set up a threshold for the identification possibility. So we kind of, when the model gets back to us to say have 90% of insurance, it is the pill we display. Otherwise, we will show we cannot recognize this pill. So that we gave the patients definitely a more accurate information instead of just to give them a guess. So right now it's kind of, if our model run on top of 90% confidence level, we display that. Did that answer your question?
Yeah, absolutely. And a follow-up from me is, what do you anticipate will be necessary in terms of a technical capability to bring that, to near like 100% identification? Is it that the camera technology or augmented reality technology or hardware needs to improve, or what is kind of a barrier that you guys are facing?
Yeah, so the biggest problem is the data. So if we get much more data, we can make the accuracies higher. Yeah. So the problem is, as I mentioned, we only have 8,000 images from NIH, and that image is one image per pill, right? So you don't have different directions, you don't have different light conditions. So it make the identification harder. So if we can get much more data as we plan it, if we can, collect the images from the patient directly and consolidate instead of using one image from the NIH, we can improve the accuracy much more.
That's great. Another question from the audience: Are these applications going to be open to the public, or are they currently being restricted to specific clients or agencies?
Yeah, that's a great question. So those applications so far is still in the beta stage. So we're still withholding that. We're not released to the public yet. Again, so there's more. I would say we're way beyond the proof of concept now. We're probably at the first MVP stage, so that we know that it doesn't work, and we're still kind of try to make it stable, try to make it also applicable to potential customer needs. So we're still doing that phase of development. But we're pretty excited about this, and as I mentioned earlier, we applied patents for this PillSafe as well as the counterfeit drug detection, and we're actually working on the next stage, make it available to the public.
And when do you anticipate that might happen? Do you have a goal set where you would like to make the applications public within, a year, or how long do you anticipate the gestation period to be?
We don't have the date yet.
Okay.
It's a complex. I think I don't think Ben mentioned this one. Actually, all the developments are invested by the company itself, right? So we don't have any external investment. So to make it public available, I think technically it's already available. We are pretty confident about the capability of the applications, but in terms of the other things, make it production grade, high availability and security, those kind of things. Probably we need some support from external. That's what we're working on at this moment.
That's probably tied up to, I thought John just had another question from the audience. Is PillSafe working with any government agencies to deliver solutions? Yes, actually that's another way we want to have provide value to the government is we definitely welcome any of the government agency if you see there's a need or there's applicable situation for apply this technology over. We'll definitely welcome the connection and then can talk to them more so that we can customize this application to agencies' needs. That's actually one of our main goal is really using this proof of concept or beta or MVP to drive some of the adoptions at the government sector. So definitely, if we know any agencies have the need for that, I really welcome to pass out our information over, and we're definitely looking forward to the detailed connection.
Well, thank you all for taking the time to present today, and for all of our participants for joining us. Again, we will make this webinar available on the ACT-IAC YouTube channel and on the ACT-IAC website. Please stay tuned for more information about upcoming webinars. We will definitely be showcasing some more of the innovations that came out of Igniting Innovation. And thank you to Precise and to ICF for helping out with today's webinar.
Thank you so much, Mark.
Thank you.
Thank you.
Bye-bye.